Okay, welcome everyone to our RChain Education Session for Tuesday, May 26th. So let me grab the agenda again here, put it in the chat. Let me share my screen. Okay, so last week, Arthur was doing his superb presentation on his work that he's been doing, but just as technology always goes, there's things come up. Arthur, were you able to resolve some of the issues that you had last week? Okay.
Yes, I think so.
Okay. Do you want to finish up, or how do you feel?
Yeah, sure.
Okay. So let me allow you to take control, and it's all yours.
All right. Okay, so where we were last time is I'll just start a new auction. I'll just be cutting and pasting. So new auction was just a hash of the data that was import. Then open the bidding. Okay, that's open. Then I can post a bid. So for this auction, Church will do $100. We generate the blinding value. That's just a random number. The commitment and the range proof is generated on the in the browser. This is the ID of the bidder that I'll just copy over. And then we'll just do another one for showing. Let's make it $200. We'll post that bid. You get another blinding value.
And this blinding value is only visible to sender of the bid, right?
Yeah, right now only the bidder knows these values. Yeah. So that's
it must remember this value, or
yes.
Okay.
Yeah. So then once the bidders have submitted their bids, then we close the bidding. So close bidding. This just changes the state of the auction so that we can now open bids.
And who is allowed to close auction?
So this is the auctioneer. So at the beginning we had an auctioneer that the auctioneer sets the opening and the closing.
Oh, okay, nice.
And it could be done by time, or it could be done by a number of bidders that have submitted. So now it's closed. We can now open the bids. So this was $100, and I'll put in the blinding value. Yeah, as I said, the part that I haven't implemented is these values are now being sent in the clear to the contract, but they really should be encrypted with the auctioneer's public key using the elliptic curve integrated encryption scheme. But I haven't implemented that yet. So these two values right now are being actually put on the chain. But the server, calls the cryptographic server to verify that the bid has not been changed, right? So it actually uses these two values to create the Pedersen commitment to make sure that the bid is not being changed. And then we'll do the next one, which was for $200. And that's the blinding value. Open that bid. Okay, that one also passed. Then you end the auction. When you end the auction, that's when the auction orders the values, and then computes the difference between each of the ordered values, and then creates a proof of the commitments to the differences, and it also creates a proof to the ordering. And then this over here is the winner. This is the highest bid here. So the highest bid was the one that did the $200. And then you can see this $100 here would actually be encrypted using the auctioneer's public key, right? But right now, I'm just putting it on the blockchain. And then when you verify, this is just a verification step to verify that the proof that the auction was executed correctly is correct. And that's when that's the verification that this was actually the bidder ID, and that is the actual bidder ID, which was this one here, right? That one was the highest. So that's it.
And you can also get the list, ordered list of all the bidders, right?
Yeah, these are the bids for an auction. Yeah, you get the commitments in the proof. I'm not the verification could output more data, but I'm not outputting that right now. It's on the blockchain.
Oh, I see.
But these are from auction.
You said that this blinding value you can encrypt with the public key of
the auctioneer. Yeah.
Auctioneer. Yeah. Where is the private key?
Yeah, it's in the private key needs. I mean, the scenario that we imagined was that when the auctioneer creates the auction, they send out emails to the bidders, and that email that you send out could have the public key of the auctioneer, but the private key has to be held off chain. Part of just like we call out to the cryptographic server to do the proofs, we'd actually also have to call out to the cryptographic server to decrypt the values that are sent.
So I see this as a like central place, right? So if all the validators want to execute exactly the same thing, they need to call this server, right? Which holds private key.
I think that, yeah, yes.
This is a problem for you cannot decentralize this step, right?
Yeah,
can you do it? Can you do it in some other way? I'm thinking.
Yeah, I haven't. There's two concerns to me. The one is needing to generate the proofs for the auction that needs to be done by the same server. And then the other question was, issues. How do you deal with the private key for the auctioneer? Yeah.
Okay.
Yeah, I'm not quite sure where to put private data and how to do with that. But I think if we think of the tuple space as storage, and you do puts and gets into the tuple space. But at some point when I was rethinking the HTTP, is that the HTTP call out may not be such a good idea. The crypto server should be listening on a name, for example, and then so the HTTP thing calling out, I think, is not necessarily the right way to go. I have to rethink that a little bit. So you will have multiple servers listening to the same name, or the same server listening to the names on multiple nodes. But there is this centralized function around the cryptography. Yeah.
Yeah. So yeah, I'm thinking maybe instead of private key, maybe there can be some kind of well, like a multi-sig that is protected with unforgeable name and not with private key, but it doesn't give us privacy.
Right.
Yeah.
Yeah, I mean, if you have multiple parties, yeah, it's if you have multiple parties and they have to encrypt and decrypt stuff on chain, somewhere along the line you have to, allow if you can't put that on the chain, then you have to get that off chain.
Yeah, so something to think about, definitely. Yeah.
Yeah. Yeah, at least I was able to get through the scenario to putting together all the pieces of going from the browser all the way back to a server that can do the stuff. So I think it's something I can iterate on.
Yeah. I mean, this exposes, what are the some underlying problems or that needs to be solved. Yeah.
Yep.
Nice example. Yeah. Thanks.
Okay, cool. Thanks.
Yeah, great. Thank you, Arthur. We appreciate the presentation. Okay, so let's take a look at our agenda here, see what else we've got going on. Bear with me. Okay.
I have some Scala stuff.
Oh, okay. So okay. So Tomislav, yeah, feel free to take it away.
We were discussing about effects, and with Bill and NetZipper, I was also have some discussion about how can we simplify our dependencies, and how can we extend existing code. So I have an example which I think is like easy to wrap your head around. It's just about lists and option, and we can generalize this and see how this relates to effects, or how we can express dependency not directly on instances, but we can have dependency on trait or interface. And also it's connected to the story of monads. Let me choose a bigger font.
Yeah, thank you.
Is this big enough?
Yeah, that's probably better. Or is it maybe one size up, perhaps, for our viewers who watch this on video replay?
Yeah, and I don't have too much of code, so yeah, I can make font bigger. So I have an example, very simple, with a list of integers that we want to filter in some way, but what this filter gives us is not directly true false, like a boolean, like direct value, like primitive value. It's wrapped in option type. So this is exactly like some kind of effect, the option type. Last time I was not very precise what is option type. It can be one of these two values, one of these two instances of some class or non-class. So this is what extends the option type. So in our example, we have this function that maybe, you know, it cannot give you directly information about true false. This information will be packaged up in this option type. So we cannot directly use filter on a list. We have this like complication, right? We have this value, this Boolean value in another type. So for this purpose, we can use this filter A function, which needs some dependency, right? Which needs some implementation on a list type and on the option type. So with cats library, we can do this in this way. First, we can specify we can import the syntax which in cats library, and with Scala this means we are importing some implicit instances of these classes. So this gives us this filter A function. For example, if I comment out the syntax thing here, I'm losing this function here. It's not available anymore. And also, there is no sum function that I can call here to construct this option type. So this is the first part of cats that gives us some kind of extension on this list. Is this make sense? Before I go further.
Yes.
Yeah.
Let's go.
Mm-hmm.
So I'm using list and option as like very familiar types. So that there is nothing fancy here. So this is Scala list and this is Scala option. And so when we apply some values to this example function, we can get different results, right? Because we are filtering if this value is greater than 0. So in the first example, we will get sum of list of values that are bigger than 0, and in another example, we are filtering and we are getting only the positive values. So.
Could you explain because I'm comparing with TypeScript, the return types, why is there option and brackets? Why can the function example1, why does not it return just a list of int?
Yeah, it doesn't make too much sense, right? Because if you don't have any value, you can return empty list, right? But I'm doing this on purpose because I want to show, I want to abstract over these types, right? So now these are fixed type. This is the list and this is the option. But this doesn't have to be the case, right? So, for example, I can do almost the same thing with this function. I can say, I don't want to use option here. I will introduce the variable, right? So instead of saying, oh, this is like option type, like specific class that exists, we can define a variable, just like variable that we are using for the values. We can define variables in the type level, and this is exactly why how this works. So we are saying this variable f is not just like normal parameter or parametric type. It's something that accepts another type. So it can be option, it can be list, right? Because option accepts something, a list accepts something. So this F represents this list or option. It can be both of them. And because I want to package up this in this F type, for this purpose, there is like a special interface which is called applicative functor. And this applicative functor has this function pure. So what I did in this function, I removed special or direct class, and I replace it with interface, right? This is like a normal thing, what we are doing in other languages, right? In TypeScript, you're just, in place of class, you're putting the interface. The special thing here is that this interface is not directly interface. We are saying this is like a variable that we are assigning the interface, because we want to say that this interface is higher kind of type. It's the type that accepts the type. And I can write this in another way in Scala, because this is like syntactic sugar. So I can do this. I need to specify this as a variable, because this is the way how you introduce variables in types, right? You have the brackets in the name of the variable, of the defining type. In TypeScript, these brackets are used, right? So when we have this F, the complete definition is implicit type, implicit value that we need to specify for F. And we can say, well, if you give me this implicit value, which I call AP, which doesn't, the name we are not using, but we are saying this must be applicative of F. So this is completely the same code, and I don't need here this. So this is very important to understand, because this is just the syntactic sugar for this kind of syntax. So if you see this colon something, this just really means I have another argument that I need that it needs to be supplied for this function. If we have more than one, we need to specify, well, monad is not a good example, but maybe we have some kind of timer. So this just means that we have another argument here. So this is how can we read the Scala code, right? We just see what are the dependencies of this function. So now this function doesn't depend directly on option type. It can be any type for which we have applicative instance, any type. And you can ask, oh, but how this looks for option type? You know, how option type implements applicative. So what do you think? What is the pure in option type? So option type can have two constructors. It has two constructors. Some to put some value inside, or none, which doesn't accept anything. It just say, you know, I don't have a value. So here we are using sum to package up this in option type, and here we are doing the same thing. but more abstractly for applicative. So this really gives us the answer, right? Because pure and sum are completely the same. So option type, it's implementing applicative is just the calling the sum. This is the pure, and we can see this when we go to the instances of. Let me go here to the option instances, and we can see here that pure is implemented with together with the whole traverse class, and you see here that pure is really just calling the sum of option type. There is no magic, right? It's just interfaces and classes. So applicative is implemented for option type in that way that pure is calling sum. And in our code, we are calling pure on many places, right? Let's find some finalized storage. Last finalized file storage, and you see here pure is called on multiple places. So we are not saying what is f. In our case, f at the end this will be the mnemonics task. This will be the asynchronous operation. But we are not saying here what it is. We are just saying, oh, package up this value in whatever implementation this will be. Package up this in this f type. So this f practically can be option, right? And we will so this code will just call sum and package up this value here. So what we want with this tagless final style, we don't want to say what is f. So for f we are just saying, you know, f must be applicative, f must be a monad, f must be that and that and that. We are just specifying dependencies. So that at the end, when we want to run the program, we will say, oh, for this f, you know, implementation is, you know, this, you know, concrete interface, a concrete instance. So, and this is exactly what is going on in this example. For f, so this another example of this function is, we are not saying what is the return box in which will return the result. We are just saying it must be applicative. So here we only need to import this traverse interface for a list type, for a list for a list type, yeah. And this is the instance that we are interested that we need for this filter A. But return type is not specified. It's abstract. So in this example, you see what is the result. It's different from the previous results, right? This is somehow magically inside ID. So what is ID? You know, how this ID came up here? Because and then of course this result, it seems like it's not packaged up in anything, right? It's just normal list, and here we have something we have this f, so it must be something. So there is another thing that is going on here. So let's see what can we do. If we put this import for option here, so the only difference between executing this code and this code is that we are adding some additional imports before executing the function. So we are just adding some kind of, we are putting something into the scope. And when I execute this code, we get this result. And this result is completely the same as this. And what happened with this ID? This ID is the most simplest box. It only has a box ID. It doesn't have some other other case, right? And in Scala, this is always available, right? You can always package up something in ID, right? Whenever you have this F type, you can have applicative for ID. It's just that simple, right? You put something inside this type, and you can always extract whatever is inside. And Scala is doing this like automatically. And when you have something that is ID, Scala is unpackaged up. It's just extracting what is inside and say, oh, this is the value inside. And when we introduce in scope applicative for option, because this will bring applicative option implementation, then this function, which we can inspect for implicit in IntelliJ with Shift Control P, we can see what kind of implicit arguments this function is using. So we are seeing, oh, this is not all of the arguments for this function. We have additional argument, this option implementation. And we can click on that and go directly to implementation. And I can also prove you that this is the case, because we can do this manually. We can say implicit value for this applicative, and we will use our standard instances for option. And we can execute the code again. And everything works the same. So the point is how to put additional arguments to this function. So we can also do another thing. We can say, let's do this directly. So we don't need. I said implicits. Implicits are just an additional arguments to the function. So let's put these additional arguments here and execute again. Oh, exactly the same. So we are playing with this additional arguments to this function. This is what this syntax is doing. This another like hidden arguments that are floating in our scope, right? This is what Greg is saying, that we need to imagine something that this doesn't exist, here. It's not written here. We need to imagine that this exists in the air, right?
This is what we call a purification, right?
Sorry?
The purification of argument from I'm not sure. I'll just check on I'll check and ask my question again.
Mm-hmm. These implicit arguments are they're created to so that you can you don't need to specify these arguments all the time, right? You can just say these instances that I have, that they are just in the air, in the scope, and I can freely use a function without specifying it, right?
Oh, okay. Yes, I wanted to say querying.
I see.
This is what you're doing, right?
Correct. Mm-hmm. Yes.
Okay.
Yeah. And this is not exactly the carrying of the functions, right? Because it looks somehow like that, but in Scala this is not the carrying function, right? Because well, maybe it is in a way, because what does it mean if we have this kind of function? When we have function with 2 arguments, this is like a strange thing, because you cannot apply the first argument and get the function to supply another argument, which will be is exactly what carrying the function should be. But in our C-like languages, we don't have this, right? We have this like a tuple, but it's also is not a tuple, so to be even worse.
I get it.
But you're right in a sense that if we write in Scala functions like this, then this really is like carrying function, right? We can call it with 1 argument, and we will have function with another argument. So in that sense, this implicit can be like a carrying, but it's not directly, right? But it behaves in some way, because you these implicit arguments must always be at the end, and they must be together, and they're like very specific syntax. How can you write implicits?
So you would use R2A in favor of R2 to have some kind of abstraction around the type.
You mean when you're calling the function? Between these 2 cases?
Yes.
So this is not very nice. If you need to specify like in this way, then you don't get anything special. But maybe you will have situations when you must specify. I will show you 1 example. I want to have this situation. So in this situation, if I want to execute the code, I will have this ambiguity between instances, because what to use? So we have something from list, we have something from we have applicative instance for the list, we have applicative instance for the option. So Scala is saying, what do you want? I don't know what do we want to put to this additional argument. So I can choose what I want to use. Do I want to use option and return return result inside option, or I can use a list and return result inside list? So what is nice with this function is it works with any instance of applicative. So right, you can have this part of the code completely abstract over which instance you want to use.
And can you run it with option and only -2 and -1 as values?
As option instead of this list, or
no, in the line 37 you choose that one, and then you just send negative values you will get some sort of empty result.
Yeah, in the option type. Empty list, package up in the option type.
So you will be able to match it with empty in some test case.
Yes, yes.
Okay.
So we can also do one step more, right? So we can say abstract input and output, right? We can define this function which is not using list. We can say, oh, this is a G. So we are completely abstracting this function. Nothing is this function will be like specific to any structure. We are just saying, oh, F must be applicative, you know, and for G, what we need for G. So we will just define another variable. So this G is also some kind of box. And what we are using for this list, I already have here this traverse filter, right? So this G, we are saying, oh, it must be traverse filter. So let me introduce, I will import just the trait, and I will now remove the specific instance, and I will say I'm returning G inside. So now we have function completely abstracted. There is no mention of list, option, or anything. We are just saying that for F we need applicative, and for G we need traverse filter. And let's see what is traverse filter. Traverse filter gives us this filter A function, right? So this means traverse filter gives us this filter A function, and applicative gives us pure, which is used in this function, is not F. So there is no magic. We're just saying we are using whatever we specified in our dependency, our interface here. And we can use it in the same way. So if I just execute this code, of course, I didn't say what are the implementation for traverse filter list, because I'm pushing the list here. So I must say what is the instance for the list. So I will use this one. And because, and this is like a list and list. And because I'm using for both, so I'm importing instances for the list, and this list is now used for both of these types, for F and for G. And if I want to specify, for example, I can do this. I can use option here. And now what will be the result? And here I will just use one value as an input type. So I'm using the sum as the input also. Do you know what would be
the something like empty, but I'm not familiar enough with Scala.
So yeah, you're right. It must be something that is packaged up in this option type, and because this is -2, it must be empty in the result. So okay, why don't option give me traverse? Option should also have traverse. traverse filter. Not exactly sure. I'm not exactly sure why this doesn't work and this work. But this is the result. Sum, because we are this is our f, and g is also option, and we don't have the value, so it's none. So we are just playing with dependencies, right? What are the f? What are the g? And these are just arguments to the function, right? And the same principle is really the whole point of this tagless final, right? How to work with interfaces and only have implementation or instances on the edges of our program. For example, in our case, node runtime. When we construct many of this stuff, for example, the code here. Now you can recognize what is going on here, right? We are specifying these implicit variables which are used in these functions, right? So when we take a look what implicits are used in setup RSpace, this one, and we can see RSpace scheduler. Okay, scheduler is not used here. Oh, execution context should be the scheduler. The span, block store is not used here, and also the block tag storage is not used here. It's used in runtime. No, it's not used in runtime. So it's probably a reporter. Yes. But the logic is the same, right? We are creating some implicit in scope, so we can use these functions, right? Because they're specifying their dependencies here, right? So this function is saying, oh, but to call this function, you need all of these implicit arguments to be specified. So I also wanted to show how list and option can also be seen as effects, right? There are some kind of containers, and they are implementing these interfaces that we are calling, that cats are specifying because they are very useful, like the monad interface. Like if we are specifying monad as dependency, we can use for comprehension in Scala. So it's all about, what you have in your scope. What kind of effects do you have?
Very good. Thank you, Tomislav. Yeah, one question. All this relates back to, it's referred to as the Zio environment from.
So Zio is Zio is like giving you some instances. So what Zio is saying, for example, like in simplified way, or more like in example case, Zio is saying, don't put too much thinking about this execution dependency, and just forget this one part of type variables, right? And use zero directly. So from this example, it can say, this can be like saying, oh, don't use like applicative in your abstract applicative. Use list directly, right? So zero is like specific thing. So in this example, list would be zero. So what John is saying, you know, oh, this asynchronous execution is very complicated if you're working with interfaces. So you can use some specific stuff and it will be much easier. So in that context, this is what he's saying.
Okay.
So instead of having this F completely abstract and, you know, it can be whatever you want, you just need these two implicits, these two arguments. He's saying, let's use some specific like already built-in type and work with this type. So in this case, we are not specifying this as an argument to the print function. We are just using directly our zero type. In the example here, this is like directly using list and not saying, oh, this is something abstract that is, you know, we only need traverse, filter, or applicative. So this is what is his point, to simplify this and just use the zero type directly. So he's saying, use this instance without abstraction, you know, because it's easier to use. Which has some point, right? It's really easier because you have less variables on the type level. So, you know, a Scala will give you more nice errors on this kind of thing, right? You will have less surprises, but you are constrained to the zero type, right? You have the zero type always. You cannot exchange it for something else because this is not a variable. This is like very specific type. So in this case, you cannot use in the first function. You must work with list. There is no other way to put this input argument. But in the third example, we can specify whatever we want, right? We can use list, we can use vector, whatever is implementing applicative in traverse filter for F and for G, we can use it.
Very good. All right.
I hope this is like good introduction to you know so that we can talk about the real code that we have in our RChain code, because everything is based on these basic principles.
Yeah, we're getting the foundation that we need. So when we start doing code review, it's going to make more sense. So yeah, this is great. You're methodically moving us along in a direction. So I mean, for us to be able to review code and start to understand it, I mean, what a great place that would be. So great.
For example, I can show you what I was working right now for migration to LNDB for block DAG storage. Mm-hmm. So now we have this block DAG key value storage, which works with block DAG representation. And for block DAG representation, I created these extension functions, which are very similar to Cat's syntax. They are also called syntax. So they work very much in the same way. You import some syntax. So we are now building this SDK that which will be very easy to use. You just implement this syntax and you get extensions for block DAG representation. So these additional functions are extending our block DAG representation interface. So in the same way how filter A extending this, D, this G variable, which is a traverse filter. So in our case, this is a block DAG representation, which extend with latest messages, and this is a filter which is part of this interface.
Neat. And that's what's what you're actually working on as a part, when I sit in on the dev stand-ups with the last finalized block, the DAG representation. So yeah, we're seeing development in real time.
Yeah, that's the point. Yeah,
Yeah.
I would like to
That's
that we can talk about exactly what we are working on, right?
Yeah.
Because maybe this is maybe some part is specific to Scala, but the problems are very much available everywhere. So we are not solving something specific to Scala. So.
Yeah. Well, we're coming on top of the hour, but let me just make an observation. What we just kind of did there, where we got you kind of educated us on the foundation of Scala and how to interpret the code, and then being able to see, what is the issue at hand with the RChain platform, and what code is being developed to solve the current issue. You really have to be in the know as far as what's going on with RChain and with code development. It's kind of like being at a baseball game, and it's your team against the other team, and you're really following the game and the players and how the game is progressing. So that's kind of what's happening here. So to me that's kind of exciting to kind of see how this is unfolding. So I think as far as a format, for me to get that little piece of Scala that I needed to know in order to see what is actually be building in the code base. This format, maybe we can incorporate that for future sessions, because it's like you're learning Scala, but you're learning Scala as it's being actually applied in the very moment, and that gives a sense of the import, or that tactile. You're just really in presence of what's going on. So thanks, Tomislav. That was really neat.
I like what you said. I want to answer to the question why we are doing this, right? What Jim asked, because sometimes you are reading something and this is great, you must use this, and then you realize there are cases where this is like very difficult to work with them. So if you see how this is applied and how it's useful, then it's very easy to understand.
Yeah, hopefully the viewers who are watching this later can kind of get a feel for the vibe that's going on. But it's it's so difficult at times to talk about coding with language. It's math and it's logic, and it's a challenge, but you just struggle through it in providing examples. Real case examples that are going on is the best way to most effective way, I think, in communicating something that just in normal speech is very difficult to communicate. So as far as I think from my perspective, and I'm a non-coder, being able to follow and understand, that this is it's pretty amazing. So I take my hat off to you for how you're doing, Tomislav. So let me just take over the screen briefly. And so we certainly have a format for future sessions with this real-time code experience with Tomislav. You know, that's, here, I'm trying to find my share button.
I will also post all of these examples the same as last time. I will create a gist and yeah, so you can, you know, check for yourself. And,
very good, and I add those to the description for the video. So
yeah, thanks.
This, for anyone who's watching, this was going back a couple of weeks. This is the Zio environment that Tomislav was mentioning. So that was helpful to get oriented. So let's see. So for follow-up sessions, so for next week, some last week described log related back to Scala. Theo will look for video. Okay, well we'll forward some of these items onto next week. So we and then we'll add, you know, the real-time coding experience to our list of lineup of what we can go over. So at least we're kind of getting into a rhythm now with each of these sessions. So we're at top of the hour, and I don't want to take up too much of everyone's time. So and Jim's, who's on here? I don't think Jim was able to.
Can I just share a screen for a second?
Yeah, go ahead.
I wanted to share these lectures that Greg created a really long time ago, 10 years, which was like excellent for understanding monads. And I will put the link in the Discord and with together with examples. And we can talk about this the next time.
Oh, okay.
This can be like a one of themes for the next time, because Greg gives like a little different perspective of on monads. So these lectures are very, very great.
Great. Yeah, it's great to find out about these resources. You know, they're out there, you know, just waiting to be found. Little like underneath this rock, underneath this root, you know, there's another lecture or feature or video or something like that. Great. I won't be, for anyone who's attending the developer session later on today, I won't be able to attend that. Jim, sometimes he usually attends. So if he attends, then you guys can have a session. But usually I lead it, but I won't be able to attend today. So great. So thank you everyone for attending the education session today, and I'll see you back here next week for another great session. So have a good day, everybody.
Yeah. Thanks.
Thanks.
Bye bye.